Okay, well, thanks everybody for coming back. It's the last lecture. I'm sure we're all a little bit tired. So my plan for this lecture is to briefly talk about some issues that we encounter when talking about or when working with observables beyond tree level. I kind of feel it's necessary to talk about this because at tree level, everything is spectacular and simple. And that could be a bit misleading. There are issues that one encounters at higher loops. So really what I want to do here is tell you a little bit about these issues, some way in which we handle them, and in the end, I'll get a nice formula for what the impulse looks like at one loop level. So to begin, I wrote here a reminder of some of the things I talked about yesterday in my first lecture yesterday. So the first formula here is the impulse, the delta p for particle 1. So written out in terms of a phase space integral, these are the phi's, some wave functions here, the little phi's. There's an exponential. I put back the h bar because I want to talk a little bit about what happens to it at one loop, and then it'll go away again. Sorry, you know, h bars, you can restore them by dimensional analysis once you know what you're doing. So this then is the core part of the observable, the stuff that we compute from quantum field theory. Yesterday, I talked mainly about the first term here. So today I'm going to talk about the two, so I'll give them two names. I1 will have this first term. So here's the I1, this is the first term written out, and this h bars made explicit. The I2 is going to involve this part here, the cut. Okay, so now, well, yesterday, as I said, I remembered just about to describe where this h bar cubed comes about, right? And we saw when I computed, or when I wrote up a 4.3 amplitude, we saw there was a 1 over h bar cubed and cancelled, and we are happy, right? So let's have a look at what happens at one loop. Just in the context of, I shouldn't have a 0. That's a 4-point amplitude. Okay, so I'm going to look at the one loop, 4-point amplitude, so A41, and I'll just count the powers of h bar. I'll count where they're coming in this way. I tend to do things. So I'm just going to draw a diagram. Yeah, it would be enough to get the basic idea across. It can be a diagram either in electrodynamics or gravity. Let's say we're doing gravity. We're strong. Okay, so at each of these vertices, you get a factor of kappa. In E and M, it would be an E. So each time you've got one of these, you get a factor of 1 over root h bar. I'll just count those later. There are propagators here for massless particles that go like 1 over L squared or 1 over Q squared, something like that. So they will always bring out a 1 over h bar squared. Now, these massive propagators have things like 2p dot L plus L squared. So the dominant power of h bar is 1 over h bar in these guys. Okay, so I'm going to get something like an integral over a loop momentum. Now, if I put a bar there, that'll give me a h bar to the 4th, divided by these things here, L squared, L minus Q squared. So I put bars there, they cancel the factor of h bar there. So there's this net stuff gives me no h bar. So it's these h bars here cancelled against the loop momentum. These two massive propagators, well, they're going to give me, let me just write the h bar powers for them. 1 over h bar squared. And then the kappa to the 4th also comes with the 1 over h bar squared. So just in terms of the h bars, we get 1 over h bar to the 4. So you see there's a problem. I've got three suppressing this, and I've got 4 downstairs. So something has to happen, right? There's one too many powers of h bar downstairs. Okay, so, well, we shouldn't get too stressed. You know, there's a whole other term which I haven't talked about. And what actually happens, of course, is that there's a cancellation between these two quantities. You know, that's often the case in quantum field theory. You know? If you do half the computation, well, you know, you don't expect the physics to work out, right? So we've got to put the rest of the observable in here to get the the right answer. But this is certainly a warning to us, right? So we need to be careful. In particular, this is one of the reasons why we write these angle brackets here, as there are really corrections in these delta functions. These are, really you should be using the fully correct on-shell conditions throughout your calculation. In the end of the day, when you add everything up, you have these terms, the powers will all work out fine. And then when you're doing this integration, the integration over Q, you can restrict to the simpler version, where it's just 2p dot q, delta 2p1 dot q, delta 2p2 dot q. So really, it's the integral that gets done over 2 dimensions. But inside the rest of the computation, you've got to use the correct on-shell procedure, right? Correct on-shell condition. Okay, now we're also going to be working with loop integrals, so I should regulate them, and I should be working in d dimensions. So let me just make use dimreg there. Okay, any questions about that? Yeah.
Could you quickly comment on what the underlying reason is for why you get classical contributions at all loop orders here?
Well, classical physics would be super easy if you just had to do tree calculations. Right. That should probably be a warning sign. So for example, if you computed this impulse and you just took the tree contribution from there, you'd find that the change in the momentum of particles in a scattering event would be order kappa squared or e squared. It would be just 1 power g Newton. But, that's not what happens. There's an all order in g Newton thing there. There's you'll read in some textbooks that loops always come with a factor of h bar. Now, this is true under certain circumstances, but it is not true in general. So it would be true if the only h bar in your action was multiplying the interaction. There's just one h. Well, there's a 1 over h bar, right? But if there is just a h bar multiplying your interactions, well, then each time you put that in, life would be very good. But that's simply not what happens in more general theories. So, for example, in QED, we know that the amplitude is a power series in alpha, right? And alpha is e squared over h bar. So, in one loop, you're going to get an extra R2, you get more, or you just keep getting more and more and more. So there was no reason to think that there wouldn't be classical physics in the loops. Yeah. Excellent. Yeah, I was actually meant to say something about that anyway, so it was excellent that you asked me to remind me. Okay, yeah, so one other thing. So people sometimes refer to these unwanted extra powers of h bar as super classical. And the problem here is that you have these, it's super classical because I don't know. Anyway, it's kind of not great that there's these 1 over h bars, so it's not clear why it would be super. So I'll just refer to them as these singular terms. I mean, anyway, it depends on, I can spend a long time going on about that. Let's just say they're singular and the singularities will eventually cancel. Okay. Okay, so good. Now, what I want to do then is talk about this I2. So I'm going to simplify this I2. We'll add these 2 terms together. There'll be a little bit of manipulations, and then everything will be nice. And that'll be it for the day. Okay, so let's talk about I2. Okay, so what does this thing look like? Well, so from over here, I'll just extract this term here and then start simplifying it. So we have phase space integrals. And these wave functions. There's the e to the IB. I'll set the h bar to 1 now. We know how to power count it, so I can just put it back in when I need to. And then the matrix element. So I'm going to insert a complete set of states in this matrix element to simplify my life. So let me, yeah, so I'm going to look at I2, but I'm just going to look at it at one loop. So that'll simplify things. We'll see in a moment. So I have to sum over phase space when I put in the complete set. P1, P2, T dagger. So I'm putting in the complete set here. P tilde 1, P tilde 2. Now there is this commutator here. So the P, the momentum operator can act on the P tilde or on the P. And it'll bring out a factor P tilde 1 minus P1 with an index mu. Okay, now I said I was putting in a complete set, but I'm just putting in a complete set at one loop. So at one loop, I can only put these massive particles in here. I can't put any other states in there because it will now be 2 loops or 3 loops or higher loops, right? So at one loop, there's no additional states in there, and you just sum over the phase space of the 2 massive particles. Okay, so that's a nice simplification of one loop. Well, maybe I can mention that at 2 loops, when you do put an extra state in there, that captures radiation reaction effects. Interesting. But, anyway, I don't really have time to talk about that. It is very interesting to look at these things at higher loops. Okay, so now that we've done this, I'm going to rewrite these phase space integrals along the lines of what I did yesterday. So in particular, I will notate this integral. You see that's a cut. P1 plus Q, P2 plus minus Q. So I'm going to eliminate the P primes in favor of these variables. There'll be some overall momentum conservation I can use to do one of the integrals. In the loop itself, I will call, I'll introduce a loop momentum associated with the upper line. I'll call that P1 plus L. It is going to be cut. So rather than getting propagators, I'll get delta functions. So then this thing will be, so that'll be the P1, P2 integral left over. These wave function factors are going to just become squares, non-squares. And e to the IB now will be e to the minus IB dot Q. Well, I'll need an integral over Q to make that sensible. So there's a Q integral, delta function, 2P1 dot Q plus Q squared, delta function to P2 dot Q minus Q squared. There's some theta functions here, but I'm going to leave them out because they're always going to be 1. Those theta functions of energy, it's just theta P1 0 plus Q 0. It's 1. Now there's the e to the minus I b dot q. Okay, so now the integral over the phase space here. So there's some delta function that I can use to eliminate one of the variables, the p tilde 2, and I'll be left with an integral over L in d dimensions. That should also be in d dimensions. Delta functions for the propagators, 2p1 dot L plus L squared, are really positive energy delta functions, 2p2 dot L minus L squared. So those are essentially those 2 propagators. Okay, now this thing here just becomes the loop momentum, right? So it's p tilde, this p tilde, I've written it as p1 plus L. So the difference p tilde 1 minus p1 just leaves the loop momentum, L mu. And then we have 2 tree amplitudes. So there'll be the tree amplitude p1, p2 to p tilde 1, p tilde 2, and the conjugate tree amplitude going the other way. Sorry, that should have been p1 prime, I guess. No, yeah, it's on the other side. Good. Yep. Okay, so that's the expression, hopefully. Yeah. Okay, so notice here we've got 2 trees just multiplied together, right? So these are fairly simple quantities. Okay, so I want to simplify this, this big expression now, so I'm going to keep it. And we'll simplify it for a little while, and then it'll all become nice. Okay, so simplifying. All right, so there's going to be 3 steps here. So the first step will just be a little trick with the integrals. Then I'm going to deal with the L mu that's sitting in there. And then I'll add the I1 and I2, and things will become spectacularly nice. So the first little observation is that there are certain integrals that we encounter that are going to vanish. So we might as well not worry about them. Now, already over here, we're sort of seeing the kind of integrals that that we encounter. So let's say encounter. So various loop integrals, they'll have some numerators, and we'll have massless denominators associated with the mediators, and then some massive denominators. Say L squared, that'd be I epsilon, to P2 dot L. So we get things like this. Now I've written plus I epsilon here, but these delta functions, I can think of them as being differences of propagators with a plus or a minus I epsilon. So really it's sort of plus or minus I epsilon here. You've got to be careful about these things. Well, they're not going to make a big difference for me here. Now these factors of L squared, they're suppressed relative to the P1 dot Ls and the P2 dot Ls. You can think of that as a quantum suppression, right? These L's sort of scale like a H bar, the P1 is big. So what we'll do with these things is Taylor expand. So I'll get things like L squared over 2P1 dot L, plus or minus I epsilon. So in this way, we encounter linearized propagators, which is maybe what you sort of natural propagator to get for a massive number. So that makes sense. Good. Now, on the other hand, in doing this, you pick up more factors of loop momentum in the numerator. Oh, see, say 1 plus L squared would be a more sensible way of writing that. Something like this. Anyway, it's the L squared I really want to talk about. These L squares will start canceling the massive particle poles. So this leads to integrals. So we get an integral like this, integral ddl. So just one massive pole and one massless pole and 2 massive poles. So this we can simplify by bringing out the masses. U1.L, U2.L. So here I've introduced the proper velocities of the particles. So where the momentum of a particle is just m times u. The point really here is that I've just scaled out the mass dimension. Now everything else in this integral is scaleless. So the integral vanishes in dim reg. And these are the kind of integrals that we get to throw away. This is a phenomenon that we've already seen. If you draw the sort of the picture, what's going on here, I only have one propagator between the 2 objects, still one loop diagram. So there is a contact vertex there, and the contacts are 0 in this whole game because we're working in a region where the distance between the particles is large. If the particles are on top of one another, well, the distance is not large. So we just have to rule that out. We're not consistently computing any of these effects, so we have to take b not equal to 0. You could view this, it's actually very helpful, I think, to view this in space-time. I'm doing the computations here in Fourier space, but in space-time, these propagators are just Green's functions, right? And the analog of getting a momentum squared upstairs is getting a derivative squared on a Green's function. Right? So in position space, this is just the observation that if you hit the Green's function with two derivatives, you get a delta function, which makes the two particles contact one another. That's why it's called a contact term. So this is why we get to leave them out. Okay. Good. All right, so the next step is a nice one. So there's a reduction step, analogous to what Fabrizio was talking about. This is a very baby version of the kind of reduction we could do under the integral sign. So in this expression, which I meant to call expression star. Well, you put a star here. Close enough. Okay, so in this expression, so under the loop, under the integral sign, I'm going to express the loop momentum on a basis. Okay, so there's some notation here. So these p checks are dual vectors to the momentum. So they're defined, so they p check to pi.p check is 0. Sorry, pi.p check j is delta ij. And I'm also going to define q dot this p check I equals 0. So that's a, just in case you're wondering, that is something you impose exactly. Don't drop any h bars. Okay, so there's you can find a solution for these p checks. So these p check are going to have some constant times p1 plus some other constant times p2. And then there's some amount of q. And you can go ahead and solve for x, y, and z if you want. Right? These things exist, not a big deal. The epsilon here, that's just my shorthand for Levi-Civita. P1 nu, P2 rho, Q sigma. Okay, so I'm just expressing this loop momentum on this basis. And what I have to do now is to fix the basis, the coefficients. So that's easy. So for example, if I dot the L with the P1, I'll get that A. I won't get the B because P1.P2 check is 0. I'll get a C. So I'll get P1.Q, right? Now that is minus a half Q squared. Right? That's the correct delta function. Minus a half CQ squared. And then I'll get nothing from the last term. So this is what it is. On the other hand, there are delta functions here, which set P1.L equal to minus a half L squared. And that's the kind of thing that's going to integrate to 0. Right. So we get a relation between A and C up to stuff that I don't care about, that integrates to 0. P2.L, well, it's just similar. I won't bore you. Q.L, it's a little very similar as well, but there's maybe a little bit interesting. There's a CQ squared, and the D goes away. The A and the B just cancel out. This Q.L I can rewrite in terms of L minus Q squared minus with a half, and then I have to add a plus a half L squared and a half Q squared, right? But these things integrate to 0. Those two, those just cancel propagators with massless particles, so they give contact, so I get to throw them away. And you deduce that C is a half Q squared. C is a half. That's even simpler. Okay, and the final expression then is that this L mu becomes, you look it up. Did I already lose my relevant sheet of paper? Yeah. Okay, so there's a quarter Q squared P check 1 plus P check 2. I'm reasonably certain that's a typo. I think it's a minus there. Plus a half Q mu. And then there's some stuff about the D, but the D is always just going to integrate to 0. You know, my loop integrals, all they can depend on are P1s and P2s and Qs. So if you go ahead and solve for the D, there's going to be a loop momentum running around. You know, end up with an epsilon L P1 P2 Q. That L will get converted when you do the integrals into P1 P2s and Qs, and you'll just get 0 out of that. So the epsilon just cancels away, at least when you have no spin. It doesn't cancel away when you do have spin, and that is interesting. Plus something that integrates to 0. So now this is fantastic, because it means in this expression here, I can replace the loop momentum by this quantity, which no longer involves the loop momentum. It just comes out of the integral. And that's good. Yeah, well, that's good because of reasons I will now explain. Yeah. So I will now combine well, this is step 3. Okay, so we have the I1 here. And so let's write delta P1 mu in terms of these Angli brackets. So I'll write the shorthand of these delta functions. Okay, so then we have some terms. I Q mu A for 1. So this is the, I'm just extracting the one loop part out of there. I've set H bar to 1. And now from the I2, so the d phi integrals and the phi 1, you know, those wave function factors go into these Angli brackets, and everything else is there, good. Plus, now the loop momentum factor, I'll just bring it outside. So this quantity here comes out. Quarter Q squared P check 1 minus P check 2 index mu plus a half Q mu. And now an integral. So the two delta functions, let me just abbreviate them both as delta plus. A for 0 times A for 0 complex conjugate. Okay, now this bit here, now that the loop momentum is factored out, we can recognize this as the cut of a one loop amplitude. Right? This is just, you know, so this tree, are integrated over the correct phase space. So this is twice the imaginary part of A41. Right. Meanwhile, this term here, of course, well, it's just A41 that has a real part plus I times an imaginary part. The I there hits this I and gives you a minus sign. So there's a minus Q mu imaginary part. And this term here gives you a Q mu, choose cancel, times an imaginary part with a plus. So, so these things cancel. The imaginary parts cancel out from the Q. So I can rewrite this. That should really have been a D. Delta 2P1.Q. Delta 2P2.Q. E to minus IB.Q. And times IQ mu real part of A41 plus a quarter Q squared P1 check minus P2 check mu in A41. And that's it. So you see both the real and imaginary parts come in here, but they play slightly different roles. Okay, so this is the tidied up formula I wanted to derive. And that's more or less it. We will manage to finish a wee bit early. Now, let's get back to this business of H-bars. So I told you that there was some funny business regarding those H-bars. And in particular, that this 4-point amplitude seems to have one too many factors of H-bar downstairs. Now, what's happened in this particular term is we started out life with an L mu, multiplying it, which scales as H-bar. But we've ended up with a Q squared multiplying it, and then something that's H-bar independent. So that Q squared means that there's an additional power of H-bar that came out of this manipulation for this particular term. So this thing scales classically. And it's sort of manifest for this part of the observable. This term here doesn't scale classically to the I, not visually, not right now, because it still has this Q mu here. But it turns out that the real part of the 4.1 loop amplitude has one less power of H-bar than the imaginary part. So the real part is, in fact, scales classically already. So one way to see this is the following. So one thing you can do is to use the fact that we can write propagators in terms of principal values minus there's an I over 2 delta with the hat p squared minus m squared. Okay, so that's, I mean, what I'm interested in here is figuring out where the factors of I are, right? When I take a real part of something, you know where the I's are. So there's some I's associated with the propagators. There's another I running around the place. So it is I times the 4.1 loop, which is the sum of the diagrams. Yeah, and if you look into that sum, you'll find a one loop, there's various factors of I in Feynman rules. They all go away. The only I's that are left are in the propagator denominators. So A41 is minus I sum of diagrams. So the only I's in the sum of diagrams is in the propagators, right? So that means to get the real part, I need to extract either one delta function, right? So that's minus I hits that one, gives me something real, or 3 delta functions. But if I cut 3 things at one loop, cut 3 lines, I'm going to end up with isolating on-shell 3-point amplitudes, and those vanish in Minkowski space. So the only way to get a real part out of this is to cut 1 line. Okay, so that means what you end up doing is something like this. So I'm just cutting one of the lines there. That is a 4.3. So if we do the counting in the h bars again, there is a 1 over h bar squared there, 1 over h bar squared there. There's one there. There is a sum from these vertices. Let me do this in E and M since it's the easiest thing to do. So there'll be factors of h bar associated with these vertices. And from the integral 4 powers of h bar, which will cancel these things out there. Now, we need to know what this tree is. The magic is in the tree. So that tree is just this Compton amplitude, Compton tree in E and M. Very easily computed if we choose the gauge. So I've got 2 outgoing photons there. If I choose the gauge that those photons, let's say this is line 2, they hit line 2, that's 0. It's just a gauge choice, perfectly reasonable gauge choice. Well, then it's easy to write down what this amplitude is. The tree amplitude is just going to be E squared epsilon 1 dot epsilon 2, up to a number, right? Can't be anything else. So the only h bars in there are associated with the coupling. And then this whole diagram will scale like 1 over h bar times e to the 4th over h bar squared, just 1 over h bar cubed. So that works for the real part. It doesn't work for the imaginary part because then you factorize this thing and you get an additional power of h bar downstairs. Okay, so that's the story of the h bar. They just all go away in a pretty straightforward manner when you separate this thing out nicely. Now, one last comment on this second term here. Like, oh, yeah, I have space over here. Now, its role in life isn't just to fix up some nasty business of, the classical limit. There's really a reason for this thing to be there. It has a reason to be there. And the reason is the on-shell condition. So we need P1 plus delta P1, say the leading order, plus the next to leading order, these things squared, to be equal to m squared. So that leads to some requirements that, for example, that, well, P1 squared is just equal to m squared. So we will need 2P1 dot delta P1 leading order plus, well, some other stuff. But, if this is, say, order kappa squared and these are order kappa to the 4th, this thing here is the only kappa squared term, right? So it better be that P1 dot delta P1 leading order is 0, right? And that'll work out because, at leading order, you just need this first term. And if I dot delta P1 with P1, I'll get a P1 dot Q, but that's 0. So this thing goes away. So now when you go to the next to leading order, there are additional terms. There will be delta P1 leading order squared, and then plus 2 P1 dot delta P1 next to leading order. And now there are higher order things. So at next to leading order, at order e to the 4th or kappa to the 4th, these are the only 2 terms that you're going to encounter. So they must cancel. Now, if I multiply this delta P1 by P1, next to leading order, well, again, if the P1 comes in here, it'll hit that Q, and it'll get 0. So this term doesn't contribute. This is the only term that does contribute, right? And that's why, that's essentially why these P1 checks want to appear. So to dot this thing with the P1, I will just get a contribution from here, and this P2 check will cancel. And then it's a nice exercise to see that this term here, with the Q squared, and this imaginary part, is equal to the negative of the leading order term squared. Right? And that goes through if you look into the details. So really, that's the point, the physics of the second term, if you want. it's imposing the on-shell condition. And of course, that's completely crucial for us to understand the physics. All right. So that's actually all I wanted to say. I guess there's time for questions.
So if we were to calculate, say, graviton amplitudes in some sort of vector field theory for the non-normalizable theory, we would generally have to, like, say, impose a cutoff scale for the EFT or do something where, you know, at higher loops it gets bad, or we add counter terms. And so if we're only interested in classical amplitudes, do we just avoid all that? We don't have to worry about, like, say, posing a cutoff for the loop momenta and or doing anything like that?
No. There are still UV divergences that can be present in the classical theory. So such UV divergences will appear when there are effective operators that you can add to the world line, which would renormalize those divergences. So the love numbers, for example, are an example of a phenomenon like that. If you compute these quantities, say the potential or the impulse, which is sort of the on-shell friend of the potential, to a sufficient number of loop orders, you'll find that there's a UV divergence. The only way to remove that UV divergence would be to introduce a counter term, but that's the sensitivity to these finite size effects.
And these counter terms would be in a classical theory?
Yeah.
Okay.
Yeah, that's right. Yeah.
Okay.
There's effective field theories are, yeah.
Okay.
There's nothing wrong with doing EFT for classical physics. In fact, a good way of thinking about classical physics.
Okay.
Yeah.
Are there any more questions? If not, let's thank Donal.